This next problem says determine dy dx where 2x cubed plus 3x squared y plus y cubed equals 4. So I can tell by looking at the structure of this equation, this will be an implicit differentiation problem. So the rule here is everywhere I have an x, you treat it like normal. Everywhere I have a variable other than x, I have to apply the chain rule when I take the derivative. So the first term is 2x cubed. So we take the derivative just like normal because it's a function of x. So this is just going to be 6x squared. In the second term here, I actually have a product rule. So the first term is 3x squared. So the derivative of that is 6x times the second term. Then I write the first term times the derivative of the second. The derivative of y is 1, but since it's y, I have to apply the chain rule and write dy dx. The last term, y cubed, I take the derivative, 3y squared, and then I have to apply the chain rule and write dy dx. The derivative of 4 is 0. From this point forward, it's just an algebra problem where we're solving for dy dx. So I'm going to leave everything with a dy dx attached to it on the left side. And so since this term and this term had dy dx's, I grouped them together and just went ahead and factored out the dy dx. Anything without a dy dx, I'm going to subtract over to the other side. So I get minus 6x squared minus 6xy. So dy dx is negative 6x squared minus 6xy all over 3x squared plus 3y squared. For part B, we're given the same curve, and we're asked where does this curve have a horizontal tangent line? And it says you may use your work from part A. So we have a horizontal tangent line anywhere the first derivative, this is implicit, so anywhere dy dx equals 0. So this equation will only equal 0 when the numerator is equal to 0. So I'm going to take the derivative, or the numerator of the derivative, and I'm going to set this equal to 0. I can factor out a negative 6x, and that leaves me with x because I took the negative 6 in the x, and it just leaves me with positive y. So we can see from setting the left piece of this function to 0 that x equals 0, but we can also see by setting this piece of the equation equal to 0 that we could also have a horizontal tangent line anywhere x equals negative y. So in order to find these points, because we actually need a x and y point, I can use this equation to try to figure out what that second value of x might be. So we do this because when you have two variables and two unknowns like we have here, you need two equations to solve. The first equation we used is the derivative. The second equation we're going to look at is the original function we were given. So 2x cubed plus 3x squared. Well, if x equals negative y, that's the same thing as saying y equals negative x. So I'm going to plug a negative x into this equation everywhere I had a y. And I'll get 2x cubed minus 3x cubed minus x cubed equals 4. 2 minus 3 is negative 1. And negative 1 minus 1 is negative 2. So I get negative 2x cubed equals 4. So x cubed equals negative 2. So x equals the cube root of negative 2, which is the same thing as saying negative cube root 2. So now I need to find my points. So when x equals 0, this equation tells me that y will also be 0, because I just simply plug 0 in for x, so y will be 0. So one of our points oops, my bad. Sorry, never mind what I just said. These are two different locations, so you can't use this equation. I go back to the original equation. When x is 0, sorry, we always plug it into the original function. When x is 0, I get 0 plus 0 plus y cubed equals 4. So the cube root of 4 will equal y. Make sure I did this right. 0 plus 0 plus y cubed equals 4. So the cube root of 4 is y. So the cube root of 4. When x equals negative cube root of 2, right? Everything I wrote in red, right, was the second location. I am allowed to go back and use this expression. So y will be the exact same value, but have the opposite sign. So these are our 2 points for our horizontal tangent lines.